Hey, class. Today, I wanted to just jump on and talk a little bit more about core damage, give you some extra notes. So core damage is the degradation, the physical degradation of the reactor core that prevents it from performing its function of containing the fission, allowing the fission to happen, and transferring that heat from the fission into the coolant to create steam, to spin the turbine, to spin the generator, to make electricity. So it typically involves fuel cladding failure, which that lets fission products into the coolant, right? So the first barrier fails, the first and second barrier fails. It gets out of the fuel pellet and then past the fuel cladding, and then it gets into the coolant. It can also cause loss of core geometry and impair the core cooling, the ability of coolant to flow over the material, to cool it off, to remove the heat, to prevent further meltdown. So ultimately, it involves significant fission product release, because once things start melting and all those fission products and all those uranium ceramic pellets get out, that's bad, right? And regulatory agency, the NRC, uses a term called core damage frequency. And it uses this CDF, core damage frequency, as our probabilistic risk measurement for plant safety. So CDF is the core damage frequency. That's how often a reactor will have a significant fission product release in its lifetime, or in how many years, how many events over how many years. So the typical core damage frequency for a US BWR, boiling water reactor. So the NRC will not let a plant operate if their CDF is less than or equal to 10 to the minus 5 events or per reactor year. So how many is that? That's fewer than one expected core damage event per 100,000 years. So we have to be higher than that. And most BWRs are about 10 to the minus 6 to 10 to the minus 7. So we're talking millions of years. And that's due to improvements in equipment, procedures, and the probabilistic risk assessment programs. We're using better software, we're using better calculation models, and that's helping all those numbers go up. So let's talk about Columbia Generating Station. Columbia Generating Station is based on information that I'm able to give you. It's a BWR 5 Mark II containment. The estimated CDF, which changes, as we improve things in the plant, we are at about 2 times 10 to the minus 6. So once every 2 million years of reactor operation, we could expect a core meltdown. And that estimate reflects the probabilistic risk assessment updates performed during our most recent license renewal. It includes internal events. It includes fire risk. It includes seismic risk, wind risk, all these external hazards that might matter. And so we're consistent with most other BWRs. So let me clear this. What we have typical progression of core damage. You typically have a loss of coolant accident, a LOCA. And that loss of coolant accident means, for example, our design bases, where the double-ended shear, the pipe falls out, and then we lose all that coolant from that's protecting the reactor. And then, on top of that, we have a station blackout. So that's bad, right? Station blackout means we've lost all connection to the grid. So we can't get power from any of the dams, from any other nuclear plants. We're isolated. We're electrically isolated in this situation. Normally we're not. Normally we're connected. Normally we're getting power. But in this situation, station blackout means we've become electrically isolated from the grid. and we've shut down, and we don't have any power. So we're down to batteries, and batteries only last so long. In fact, after Fukushima, we upgraded our batteries to go from an estimated half hour to 1 hour to a minimum of 4 hours of operation. So we could operate 4 hours on batteries. Then we have some transients without a scram. So this worst case scenario means we have to have an AOO that's supposed to cause a scram, and we end up with an ATWS, what we call an ATWAS. It's an anticipated transient without scram. That means the rods did not go into the reactor for the shutdown. So you can see all the things so far that are stepping through this that you would need to have happen to make this worst case scenario. Oops, my pen. And then you have to have a loss of heat removal. No heat removal. And then you have to have decay heat that continues after shutdown. You have to have a significant amount of decay heat, which means you had to have a high operating history. You had to be operating at 100% power for a long time. And then you have to have loss of core cooling, which is the no heat removal. So I guess that's redundant. And then, but that's all that leads up to cladding failure. Once you have cladding failure, the fission products come out of the uranium oxide pellets, and it gets into the coolant, it gets into the air. A lot of them are gaseous, and so it gets into the air, and it can cause oxidation, ballooning, rupture of the fuel cladding gets released, these noble gases and volatile fission products. The fuel starts heating up, it starts melting. Now, the uranium oxide fuel pellets begin to melt about above 5,070 degrees Fahrenheit. That's pretty significant temperature. And then the core geometry collapses. Fuel rods start to warp. They start to bend, sag, and then fail. The control rods may move, which can cause other problems with the fuel rods. And then worst case scenario, eventually a reactor vessel failure. So that's where you have your core or your vessel, your core here, and then your reactor vessel. There's your core plate. Your flow normally comes down and goes up through the core like that, and then steam comes out up here. Well, the fuel starts melting, and the control rods start melting, and then it starts coming out the bottom, and you end up with material at the bottom of the vessel, and that starts heating up the bottom of the reactor vessel. And then that melts through, and then you have the concrete structure, and it goes down into the concrete. And when you learn more about Fukushima, you're going to see this is where they landed. They actually had core melt coming out of the bottom of the vessel and reacting with the concrete. So all these materials breach the reactor vessel, and then you end up with core versus concrete interactions in the containment. So the core damage mechanism, the thing we're worried about is what is the cladding starts ballooning. So the release of pressure of these fission products in the fuel pellets gets into the cladding, deforms the cladding under high pressure, blocks coolant flow, worsens the heat up, and then the fuel cladding chemical interaction. The fuel starts reacting with the cladding, and we get a high temperature chemical reaction between the fuel and the cladding. Weakens its mechanical strength. We have the fuel fragments escape, temperatures rise, fuel pellets crack further damaging the cladding, and on and on and on it goes. So indicators in the control room. Things that we watch for in the control room. We have what we watch for sudden increases in reactor pressure. brain glitch. My pen is bugging me. Reactor pressure. We watch for pressure to go up, right? We watch for rad levels. We watch for hydrogen concentration and containment, which you're going to learn about later. And we watch for temperatures, if temperatures start going up. Temperatures start going up. And then we have ore levels start going down. So water levels, which means we're losing coolant somewhere. Those are the things that we watch for to be an indication of damage. And so as containment pressure starts going up, that means that something's raising pressure in containment. And that means the reactor pressure is transferring itself to containment, which means there's a break somewhere. So we're going to have we expect a drop in water levels. We expect temperatures to go up. We expect radiation levels to go up. And in that case, reactor pressure would be going down. So we watch for it to go either up or down. And what happens, so let's talk about what happens once all this, let's say that all this happens and we have core damage. Then what we have is a mixture of melted fuel, oxidized cladding, control rod materials, all this stuff, all these different metals and different materials reform into a material that we call corium, C-O-R-I-U-M, and it relocates outside the fuel assembly, which means it melts through the bottom core plate, interacts with the reactor pressure vessel, and then eventually reacts with the concrete. So we saw this. We saw the core melt happen at 3 Mile Island. Now, it didn't escape the reactor pressure vessel, but Fukushima, it did. At Fukushima, we have long-term heat removal challenges because it has breached the vessel. So after 3 Mile Island, Fukushima, we changed our fuels. We changed our fuel material so that we have accident-tolerant fuels, ATF, are being developed to resist high-temperature failure. Plants, we've added passive core cooling systems. So that's what I was talking about for those of you that were on the tour in the control room in the simulator. If Fukushima had the RCIC system that we have, where we have the mod put in so that we can run it without any power, then they would have had passive core cooling systems, because that's what that means. You don't have to have any power, and it would just cause natural circulation to happen, and it would use steam out of the reactor to spin the turbine, to spin the pump, to put water into the reactor. And then we also had our severe accident management guidelines, SAMGs, SAGs, and we have our FLEX strategy, our flexible response strategy, which is those two centers, one in Tennessee and one in Arizona. And those all help prevent or help us mitigate issues as we start to, if we were to start to experience any core damage and fuel damage and core melt. But core damage is rare. We target, like I said, a CDF, a core damage frequency of about 10 to the minus 5 per year or lower. And we keep an eye on it very, very close. We have engineers whose sole job is to do constant probabilistic risk assessment. And when we take a diesel generator out of service to work on it, they recalculate all the numbers and say, okay, how does that change our CDF, our core damage frequency? Yeah. So, like I said, it's not likely to happen. It comes from in fact, we used to have fuel damage a lot in the 80s. There were problems with people dropping stuff into the reactor when they had the vessel head off to do the refueling. So we had foreign material in there that would cause little all we need is an imperfection. So that would cause a fuel cladding blister or a divot, and then we'd have a release of fission products. In the 80s and 90s, that was significant, and it wasn't until the mid to late 90s that they started really hammering down on foreign material and on things that would minimize the core damage. Let me go back up here in my notes real quick. Yeah. So about 3 Mile Island. Here's some notes on 3 Mile Island. About 40% of the cladding reacted. So that was a significant amount of fuel damage. But even with all that damage, it didn't get out of the core, which I thought was interesting. Fuel. I was talking about fuel. So fuel can also have manufacturing defects. So they've gotten better about not having manufacturing defects. We can have foreign material get into the core that causes problems. And we can also have inadvertent localized overpowering. So we work to try and maintain flux profiles. We got our reactor vessel, we got our core, we got all our fuel, and we want power. We don't want power to be peaking on a certain rod, right? We want a fairly flat flux profile, and we want it to move throughout the core as the core ages. So we start off pretty high, and then that flux profile moves down slow. But we can have problems where if we move the wrong rod, the wrong control rod, and expose more fuel, like one specific fuel rod, we can have, oh, dang it. I'm still getting used to my pen, sorry. We could cause peaking of power. And this peaking of power can cause damage to that fuel cladding, and which could then fail. And if it coincides with foreign material or a manufacturing defect, then you have cladding damage. Yeah, so those are the notes I wanted to give you. Just talk a little bit about that and have a lecture prepared just in case I can't get, I don't know. My back's feeling better, so hopefully I'll be there Tuesday. But there you go. All right, take care.